Okay, so welcome back to the Stainless Steel World podcast. We are here on the Expo 4 at Stainless Steel World 2025, and I'm very excited as I have a special guest with me today. This is Sabina Griffith, and she is the Communications and Press Officer for ITER. And ITER, if you don't know, stands for the International Thermonuclear Experimental Reactor. It's a huge international experiment that is building a tokamak reactor to prove the scientific and technical viability of nuclear fusion as a new energy source. So welcome. We're very excited to have you here as exhibitors on the stand, also as speakers in the conference. It's the first time you've been present. I know some of our exhibitors are very involved in the ITER project. One of our sponsors, Kind, of course, is providing huge forgings and special alloys, I believe, for the ITER project. Yes. Yeah.
It's correct, Joanne, that this is the first time we come to the Steel World Congress. They invited us to be one of the keynote speakers, and we didn't really think about it for a long time. So we said, well, ITER is massive steel, so it's massive material development. So why not?
Yes.
Usually we engage in all these energy debates and climate conferences, and of course also the scientific conferences, so we have been here all day yesterday, and we were really flabbergasted to see the interest in ITER, although our stand is very modest compared to what we see around us. But we have the model of our reactor on the stand, and people recognize it. Because many of the people that are here at the Steel Conference from the various industries have contributed to ITER. I cannot repeat all of what they have provided or procured because I don't even know the words for these things. From the huge forgings like Kind and others to some tubes, pipes, bellows. And so, yeah, we were really positively surprised to see the interest, and people got really engaged. They wanted to know, where are you at, and I've seen the ITER project 15 years ago. What's happening now? I said, well, you have to come back, and see what's happening now, because we are now assembling the machine.
Yes, it's an amazingly ambitious project, harnessing fusion, which is the nuclear reaction that actually powers our sun and the stars. And the reason, of course, is that it's promising a long-term option for sustainable, non-carbon emitting energy, which is, as we know, vitally important for all of us. So ITER is the key experimental step between today's fusion research machines and tomorrow's fusion plants, like an intermediate step.
Yeah, that's correct. So for decades, mankind has looked at the sun and thought, how can we bring that power down here on Earth? Of course, we have solar panels and so, but to harness the reaction that is firing the sun, which is fusing hydrogen atoms, has been a long-standing promise. And there have been many experiments around the world that try to harness this energy. And there is considerable progress made with bigger and bigger experiments, very different technologies sometimes. There's not one technology, so there are many paths leading to this technology. But it was still during the times of the Cold War in 1985, when it was mainly Russia, the United States, and the UK. They were driving the fusion research at that time, but it became very clear that not one country alone could do it. Financially, yes, but not. They didn't have the established industry to really advance the materials and the big technologies that you need to build a fusion plant. And certainly also not the manpower. So these were some small laboratory experiments, mainly performed at universities or in smaller labs. So the idea was brought forward to Ronald Reagan and Mikhail Gorbachev, which was really surprising because, again, these were the times of the Iron Curtain. Yeah. And those world leaders, then they decided to join forces and to come up with an international project to really take that last step and to prove that yes or no, can we do it or can we not? So all eggs in one basket, and they called it the ITER project, or in those days, it was still the International Thermonuclear Experimental Reactor. Nowadays, we prefer to say ITER is Latin for the way to a new energy future. And yes, fusion holds a lot of promises. It is safe. We do not have runaway reactions in a fusion reactor. The whole waste issue is manageable. We do have nuclear waste for sure, but it's of a very, very different category than fission waste. We don't have long-lived, highly radioactive waste. And the fuel is also, we use, in our case, deuterium and tritium. Deuterium can be gained from seawater. It's a very standard procedure. The tritium is a bit more tricky. We will get the tritium from Canada. It's a byproduct there in heavy water reactors. But the goal is that within ITER, we will prove, or we will test certain technologies to breed the tritium that we will use as a fuel inside our reactor. There will be so-called tritium breeding blankets inserted in the machine, and the neutron coming out of the fusion reaction will hit the first wall, which is coated with lithium, and the neutron will sort of hit the lithium blanket and produce tritium.
Okay.
It's a very simple description of what is happening. It is some sort of high tech.
Yep.
And it really, to me, it always sounds like the famous perpetuum mobile, that we produce the fuel we are burning inside the machine. But
Yeah,
that's
so it becomes self-sustaining, actually.
exactly. So
Amazing.
yeah. So yeah.
So what are some of the key sort of milestones that have been reached with the project recently?
So we started ITER in the year 2006 on the green field. So we are based in the south of France, and it was a large forest rural area. So we had to clear the site, and it took a while. In 2010, we started the actual construction. So for many years, ITER was mainly pouring concrete, because it's not just a, let's say, reactor hall. It's not just one building. It's a 48-hectare area, so we need a lot of infrastructure to support everything, like the heating devices, the cooling technology. We have a lot of workshops where we prepare the components. We have a switchyard and so on, and of course offices. And that took a while. It took a while also to set up the domestic agencies. So one very important and almost unique feature of ITER is that our partners, and so I'm rolling backwards here. So the whole ITER organization is a collaboration between 7 partners. So there we have China, all the European Union, Korea, Japan, India, Russia, and the United States. And with all the European countries, we are 33 players on the field.
Right.
And they don't just transfer money onto our bank account and we then place the contracts. No, the whole ITER project was put on the table in the beginning, and all the partners sat around the table and they decided which share of the machine, of the project, of the technology they wanted to contribute. So, for example, we have superconductors in our magnets. The magnets play a vital role in ITER. So we are building the largest and most powerful magnets that have ever been dared to build. Really big and powerful.
I heard an amazing statistic yesterday from your colleague that the magnets are so powerful they could actually pick up an aircraft carrier.
Yes. So we have one. I mean, the whole ITER machine works with a magnetic cage. So we have large radial-shaped magnets confining and steering the plasma, keeping it afloat inside the machine. But in the center, there is the so-called central solenoid. And this beast will have capacity, stored energy, to lift an aircraft carrier.
Amazing to think of. Incredible.
Yeah.
Yeah.
And so yes, and so they all decided on. Everybody wanted to contribute to the superconducting technology, because we have developed a new generation of superconductors for ITER, and the superconductors are a technology that all the countries want to accelerate and propel, because this is very important for energy transmissions, for medical applications. There is a long list of spin-offs coming from superconductors developed for ITER. The magnets themselves, they are shared between Europe and Japan. The vacuum vessel sectors are shared between Europe and South Korea. The whole cryostat, the outer shell, the big fridge containing all the cold world, is contributed by India and manufactured in India and then shipped to France, where it is then all put together. So it took quite a time to establish this collaboration, to set up the offices there, and to really verify and make sure that all these components are manufactured to the same standards, because we can imagine that the working standards and working ethics are different in different regions of the world. So inspections and project controls was the key and essential part for many years at ITER. So, but now we have most of these, I would say all of the major big components on site. They have all been delivered, manufactured and delivered. So currently in the year 2025, we are assembling the machine. So we are halfway up with the cryostat and the cryostat base plate. We have inserted the first magnets in the lower part and feeders and so on. And we are now occupied with the vacuum vessel itself. So as we speak, so in 3-4 days from now, the third sector will go in, the fourth in January. So our new director, Pietro Barabaschi, has truly accelerated the project. So we were famous for delays and mismanagement, because ITER is highly political.
Yes.
I mean, there is a lot of reputation and money involved. So it never was, and it still is not easy to see just as a construction project. It's a very political project also. So, but Pietro really managed to reorganize the organization, and so this year is the second year that we are ahead of planned schedule, that we are within the budget constraints, and so we are still accelerating. So there's good hope that we hopefully finish before the given target date, which or year at the moment, it's 2034 when we start research operations. When we press the button, when the machine is fully assembled, when it's accepted by the nuclear regulator, when the inspections are done, and when we have pumped the vacuum.
Okay. And which parts of ITER does stainless steel play a crucial role?
Well, ITER is stainless steel. 23,000 tons. So I think it's 3.5 times the Eiffel Tower. That's the weight of the Tokamak.
Yes.
And I mean, the cryostat itself, the outer shell, which I mentioned before, it's the largest steel container ever built.
And it's all stainless.
Yes, and that itself is 3,800 tons. And so tomorrow I will give a presentation with the list of the various steels and the various sort of materials we are using. But there is a special stainless steel developed for ITER, the ITER grade steel, because ITER is a nuclear reactor. So we have to respect the neutrons, the neutron bombardment, sort of the irradiation in principle on the materials, So there is neutron shielding, which we have to take care of, and the magnetic ripples. So it's anti-magnetic material that we use, because we don't want to interfere with the original magnetic field. So there has been a lot of, and still is a lot of research going into developing materials for fusion.
Right.
But steel, and this is why it was our decision was taken within seconds to come to the steel world, because ITER is still seeing the reaction by the audience here. They seem to know us.
Yeah.
Because they all provided parts and pieces and big components to ITER, and we use the various stainless steel mixtures or composites for ITER, depending on where we look at. I mean, the cryostat, the outer shell, again, so that's the largest single steel container, stainless steel container, 3,800 tons alone. We have 316L in the system. We have borated steel. We have 430. Tomorrow at my presentation, I will show the long list of the steels, the stainless steels that we are using to build ITER.
Yeah. And do you think, is the experiment actually pushing forward material developments for other industries and applications?
Absolutely. Absolutely. I think, almost all of these components are first of a kind components, not only in regards to their design, but also in regards to material strength, material behavior. Again, we operate in a nuclear environment, harsh environment, a lot of heat exposure, and very strong magnetic fields. All this has to be considered for the choice of the best materials. And there are new test facilities built. There's one going up near Granada in Spain right now to further test materials for fusion power plants, because we know that ITER is already very harsh on the environment, on the materials. But if we talk about a power plant, it will become even sort of harsher than at ITER.
And it's interesting, isn't it? Because it's not only very hot, it's also extremely cold, because you've got the plasma is how hot? It's going around at
inside the vacuum vessel. We have to create an environment at a temperature of 150 million degrees. Million degrees
Celsius.
It's impossible to imagine this, but we have to reach this temperature to convince our hydrogen atoms to fuse, to collide and to fuse, because they don't want to. They are both positively charged, so you have to overcome the Coulomb barrier. So you need a lot of energy to convince them. And just a few meters away from the core of the plasma, that's the world where our superconducting magnets operate, behind a shielding wall. And there it is colder than on the dark side of the moon. It's almost absolute zero. Yes, we have large temperature gradients within short distance, huge magnetic fields, operating on the system. So it's impressive to see these big components there. Some of them are on our big assembly rigs right now. And again, they will move into the Tokamak pit bit by bit. But just seeing them, they are very solid and massive, and imagining that they can move, bend, and deform, and even sort of lift off under all these conditions is...
You have to make sure they don't.
We make sure they don't. I mean, our people have vast experience in maybe not so much in building. There have not been that many Tokamaks built recently, but they have vast experience in operating other machines, Tokamaks, so they know what to expect.
Yeah. So you're here at the Stainless Steel Wood exhibition, and it's I'm glad to hear that you've been welcomely received by a lot of people. Everyone's fascinated by the project.
Yes.
What are the takeaways for you from here? Who happened to meet here and to speak with?
It's the euphoria and the fascination that we see when we talk to people. Like us, we are fascinated by the project that we are so lucky to give birth to be part of the ITER story, because it's, I think, a very unique project, and so I keep telling people that even for us, going to work in the morning is not going to work. Of course, sometimes it's hard to get up, but soon as you enter the ITER premises, you know what you are here for. There is a goal. And when we explain ITER here at the conference in front of our mock-up, and we, like I did just now, give them some key figures and features and explain, and they're shaking their head, and the word we hear the most is amazing.
Yeah.
Fascinating. And I think this is what drives everybody, like children, it's curiosity.
Yes.
Can we do that?
Yeah.
It's fascinating to try. The promise, as you said in your introduction, would be enormous. If we manage to harness that energy, a lot of problems could be solved. We are not there yet. There are still some other questions to be answered, even after ITER, but we are getting there. And one of our former ITER Council chairs, when he was asked with a certain amount of criticism, wouldn't all the money you're putting on ITER, and there's big money going into ITER, wouldn't all that money be better invested in propelling renewables, sort of? And he said, well, we are very close to the answer. Do you want to tell your children that we didn't go that last stretch, that we didn't dare to try?
Yeah.
Yeah. So I think this is something in us, in mankind,
Yeah.
You see that it's within reach,
Yes.
and despite all the odds and all the physics that tell you it's going to be difficult, but we'll go for it.
Yeah, it's for the
Yeah.
betterment of humankind
Yes.
and for the entire planet,
Yes.
actually.
And we know what we are doing. So we
Yes.
have some very experienced physicists
Yeah.
and engineers,
Yeah.
a lot of them.
Okay. Sabrina, it's been fascinating talking with you. Thank you so much for speaking with us today.
Really.
Really looking forward to the presentation and the conference. I know people are coming to your stand to talk to you about it. It's been an absolute delight to have you here. We hope you come back and see us again next time.
Yeah, and I thank you, Joanne, for inviting me to present ITER here. And my last word would be, come and visit us.
Yes.
You have to see it with your own eyes. And we are open. Everybody can come, just on our website, there is a visits button. Just click on it, book a tour, or
I'm gonna do it straight away.
contact ITER Communications, and we'll take good care of you.
Lovely. I'd love to come and see it. Thank you.
Okay, Joanne. Thank you.